Everybody close. Sorry. Think we should close it for? Wait till the guard comes in. Oh. There's a little.
So who of you is going to CPS week?
HSCP. Carlos and I
Yes.
go.
Okay, perfect. So we'll see us there at the workshop.
Yeah, totally.
Awesome.
I think Ricardo's coming to this, the last thing that we heard.
Yeah, he was saying that he might be a little late because he might have a visitor on Monday, but he wasn't sure yet.
Oh, good. Is the workshop on Monday?
Yes, yeah. So you'll hear me again on Monday talk about a different topic, though.
Good. That's good. All right.
Yeah, I tried to separate it to not have overlap with the topic from today and the topic I'll talk about on Monday.
Mm-hmm. Yeah, that's right. Excellent. Yeah.
So we're almost ready, Lars.
Yep, all good.
Some coffee. Okay. Great. So, good you? Okay.
Squeeze in here.
No, I can go to that. Give people a minute. No.
6. Including the TD attendance. I mean, that's a good. Here's that strongly. That's very good. Just
If you get started, so we don't run late. Okay. So welcome everyone to our seminar series. We are kicking off the spring seminar series with my colleague Lars Lindeman, assistant professor at USC. And many of you know him from his work back in his PhD time at KTH. And he's done a lot of work. He probably is going to show us some of his work right now on the area of learning, safe control laws. We were just talking about all the things that he's interested in doing. He was a postdoc as well. I do believe that he was at the University of Pennsylvania. Is that correct?
Yes, exactly.
Exactly, perfect. Were you there with George Papas?
Yeah, I was with George and also Nikolai Matny, who I did this work that I'm presenting today with.
Great. Well, in addition to the research that he's going to show us, he has been a recipient of some awards, the Outstanding Student Paper Award at the CDC, and also the Student Best Paper Award as co-advisor at also the 60th CDC. When was that? Was that last year?
2021.
Oh, 2020. Well, congratulations for those. And he has awards, including the Best Paper Award at the 2022 HSCC. Some of us will be there next week, and also an American Control Conference Best Paper Award. So, with that being said, the floor is yours, Lars. Thanks for coming.
Ricardo, thank you so much for the kind introduction and also the invitation. So I'm going to talk about learning safe control laws from expert demonstrations, but I want to tell you a bit more about the broad research area that I'm working in and the agenda that I have first for like a couple of minutes. So I work on autonomous systems very broadly. And as you know, autonomous systems are control systems that operate autonomously in complex and open-ended environments, right? They perceive the environment that they operate in. They reason and learn from data. They may assess risk and uncertainty, and they make decisions and compute control inputs to achieve a wide variety of tasks, right? In this broader area of autonomy, the applications that I'm interested in and that I'm inspired by is basically in autonomous driving and robotics. More recently, also in wildfire prevention, as you know, in California, that's a hot topic, as well as in warehouse applications with some industrial collaborators. But you can imagine there are many other applications in autonomy in aerospace, agriculture, smart cities, and in healthcare. And all of these certainly highlight the importance and the potential impact that autonomous systems research may have in the future. Over the past years, really the availability of data and the advances that we have made in machine learning and AI has accelerated the progress that we have made to build these autonomous systems. And I've shown 3 examples here that you may know from Boston Dynamics, the robots they have, Tesla cars, or the drone fleet at the Kumar lab, where these autonomous systems really perform highly challenging tasks with ease. And indeed, from these demonstrations, one could really claim that autonomous systems are a reality, right? However, the question that I would like to ask is, do we really have all the theories and also computational tools in hand to build autonomous systems that are also safe? And I would argue that the answer to this question is no, simply because at the same time, we've seen a lot of failed demonstrations. I've shown a couple of videos here, again, Boston Dynamics robots crashing, Tesla cars colliding. We've seen this multiple times, and drone fleets collapsing, right? So these systems are not necessarily safe. And part of my research is on, or very broadly, my research is on designing verifiable control frameworks, which includes safety for autonomy, for autonomous systems, along with efficient computational algorithms. And basically, my group is working on 4 different thrusts, so to speak. One is on data-driven control. That's what I'm going to talk about today. I work on system verification, multi-agent systems, and more broadly, formal methods and control and risk-aware autonomy. Just to give you some more pictures that you get a feeling for what I'm doing here. Like I said, data-driven control is what I'm going to talk about today. How we can learn safe control laws from expert demonstrations. System verification, I focus on statistical verification. For instance, if you have a system that you observe during runtime, can you predict failure modes with confidence, so with high probability, right? Entering failure modes, so to speak. And multi-agent systems, temporal logic, some of you are familiar with it. How can we plan and control multi-robot systems that are temporal logic constraints? And more generally, like I said, formal methods-based control. And for instance, here, I show some work where we consider temporally robust controllers. So a lot of people think in terms of spatial robustness, robustness tubes, right? But one can also think about being robust against perturbations in time, temporal perturbations. And lastly, risk-aware autonomy, how we can make decisions under uncertainty. And this is actually a topic I'll talk about in the workshop on Monday. So for those of you who are coming, they will learn a bit more about this. So in summary, my research really provides a formal and computational approach to systems and control theory. And I want to show you one instance of that today, which is on learning control barrier functions from demonstrations. And like I said, this is in this research thrust. Okay, so what we want to do is we want to look at the safe control problem here. So very high level, without using any terminology, we say that the system, for instance, this robot here, is safe if we can control it to stay within a safe declared set calligraphic C. So if we have this blue region over here that we deem safe, then we would like to find control inputs such that the robot always stays in there, right? And as you can imagine, this is a very well-studied problem. There's a lot of literature on it, starting from handcrafting safe control laws, maybe by even cooking up Lyapunov or barrier functions, right? However, these are usually limited to simple system dynamics, mechanical systems, for instance, or they don't even have any safety guarantees, right? On the other hand, there's a huge body of work on sum of squares programming approaches, HJB reachability analysis, and more from the CS community, discrete program synthesis. However, here, the underlying issue is that solving these instantiations, these formulations, has scalability issues, and it often requires approximations. And then what is very heavily utilized, also model predictive control, very successful, of course. But with MPC, it's that you, during the execution of the controller, it may potentially require heavy online computation, right? So it may be not as resource efficient. So in summary, it's really that finding safe controllers is a challenging task. And the starting point of our research was we were asking ourselves, can we leverage data which we have at hand a lot these days and machine learning to find and learn these controllers, okay? Now, what motivated our works was basically three observations. If we look at these three examples over here, then at first these seem to be very different, right? They're different in terms of their dynamics and different in terms of their operating environments. However, what I'd like to argue now is that in order to reason about their safety, these examples here share some key properties. A, these systems are really data rich in the sense that it's easy to get access to expert demonstrations that exhibit safe system behavior. For instance, if we think about autonomous driving, it's a reasonable assumption to have expert demonstrations that show how to drive a car safely, right? Second, the dynamics of all of these systems, they are inherently complex. They're nonlinear and potentially even hybrid, as in the case of these bipedal walkers here, right? But on the other hand, the dynamics are quite well understood in most of the cases, or we can at least identify accurate system models that we can then use. And that's exactly what we want to use here in this work. We want to use the availability of expert demonstrations of data together with known models to find safe control laws using a machine learning approach. Now, before going into the details, I want to give you a high-level overview of the approach and the idea that we present in the line of work. Assume that you know the dynamics of the system. For now, assume that you have a simple ordinary differential equation that is described by the function f and g, and that you know f and g. And we can relax that later. In fact, we will, or you can consider a hybrid system. But for now, assume that you know the simple ODE, right? Or the parameters that describe this ODE. At the same time, we assume that we're given a set of expert trajectories. These are these spaghetti trajectories that are shown over here, right? And they're assumed to be safe, meaning that they evolve within a safe set, calligraphic S, that is denoted here by this red box, okay? And what we will be doing is we will feed these two things, the model and the demonstrations, into a constrained optimization problem that we use with a goal to learn a safe control law. In fact, what we will be doing is we will be learning a function that under approximates the operating region of the experts, here shown in blue, and that has the nice property of being forward invariant, meaning that whenever we start in this blue set, we will be able to synthesize control inputs to stay in there. And the contributions of this line of work is that we come up with efficient algorithms to do so that enjoy safety guarantees. We show how we can deal with model and state estimation uncertainty, and how we can deal with hybrid systems, even with some class of hybrid systems, I should say. Okay, so the technical machinery that we're using here in this work are control barrier functions. I think many of you may be familiar with it, but I'm going to briefly recap what these are. So assume you have this system, dynamical system described by the ODE, potentially input limitations, and assume that you're given a function h that acts on the state of the system, for instance, position, velocity, whatever you want to constrain, right? And then let the safe set calligraphic C be defined by the zero superlevel set of this function h. So all states for which h is non-negative constitute our safe region and constitute this blue region over here. Now, what do we need to do intuitively to ensure safety? Well, whenever the robot is on the boundary of this safe set, we need to find a control input u, or we need to be able to find a control input u, such that h dot is non-negative. And by the definition of the safe set, which is defined as the zero superlevel set of this function h, we then know that it will be safe, because the system will either move inside if we can find such a control input, or it will traverse along the boundary of the set, but it will not go outside. Okay. And this intuition carries over to the notion of a control barrier function. So we basically say that this function h is a control barrier function if for each state in our set B, calligraphic C, we can find a control input u such that h dot is lower bounded by minus alpha of h of x, where alpha is an extended class K function. So it's a strictly increasing function that is 0 at 0. And the 0 at 0 is important because on the boundary of this safe set, h of x is 0, so that the right-hand side becomes 0 on the boundary, so that we recover this h dot condition, okay? Now, one important thing to note is for these input-affine dynamics that I've shown here, where the input appears linearly in the equation, this h dot becomes basically this equation, the product between the gradient of h and the system dynamics. And this is important because if we have found such a control barrier function, then synthesizing a safe control input is a linear program, basically. One piece of terminology in the rest of the talk, I'll refer to this constraint here as the CBF constraint. And like I said, if we can show that h is a CBF, or if we can find a function h that is a CBF, then h can act as a safety filter and life is good, right? However, the bottleneck and the challenge here is really that CBFs are hard to construct. It's a really difficult problem. And that's where we started basically thinking about, can we instead learn these from demonstrations? Okay, so let's get back to our spaghetti trajectories to these demonstrations here. And let's pick a data point xi from our demonstrations, all right? And what we do next is we put an epsilon ball around this data point, which is basically this small orange ball over here. And in fact, let us do this for all the data points that we have from our demonstrations. And let's take the union of these so that we get this orange donut that I've shown over here. And that's what we refer to as the set of safe states, okay? Where we have expert demonstrations and we put these epsilon balls around, then we get safe states. Now, for our algorithm, we not only need safe states, but also unsafe states, okay? So assume for a second that you can sample unsafe states around the boundary of the safe set, here indicated by these gray rings that are on the boundary of the safe set, okay? I'll talk a bit later about how you can do this computationally. For now, just assume that you can obtain these samples on top of your expert demonstrations, right? For 2D problems, these are usually really easy to obtain. And I'll present an algorithm later, okay? The bottom line is we have a safe set of expert demonstrations, and we have an unsafe set considered of points that we have sampled in some form around the boundary of the safe set. And with that, we can write down our optimization problem already. Some piece of terminology, the CBF constraint, this h dot plus this class K function alpha, will denote it here simply by Q. So Q will denote the CBF constraint. And the optimization problem that we write down is the following, and I'll walk you through it slowly. So first of all, we want to find the barrier function h, right? So we need to parameterize this function by a class of functions here, calligraphic h. For instance, this could be the set of neural networks, one example, right? And we want to minimize the complexity of the function for obvious reasons. Now, the important part here is that we have 3 types of constraints, okay? So the first constraint acts on the unsafe data in this gray region. Well, we want to ensure that h for the data points in this unsafe area is negative. In fact, it's strictly negative and upper bounded by minus gamma, where gamma is a positive robustness slag. Okay. On the other hand, for all safe data points here in this orange region, we push h to be positive, again, strictly positive, and lower bounded by this slag gamma as well. Okay. So by the combination of these 2 constraints, we make sure that the 0 level set of this function h is somewhere here on the boundary between the gray and the orange region. And on top of that, we enforce a 3rd constraint where we use the expert action that we assume to also have collected on the CBF constraint. So for all safe data points, we enforce the CBF constraint to be satisfied, and again, robustly satisfied with some slag gamma, okay? Note here that the use of the expert action takes out a lot of the complexity. So we can later show that under some assumptions on the function class h, I think I'll do this in 2 slides, this can even be a convex optimization problem because you assume to have expert actions, okay? For now, just assume that you can solve this problem and that you have found at least a feasible solution, okay? Now, if you have a feasible solution, then this solution is a safe control barrier function if 3 conditions hold. basically, if the data points are dense enough, the functions h and the CBF constraint q here are smooth enough in terms of the Lipschitz constant, and the robustness slags gamma are large enough. So the way you can envision this, just to give you a high-level insight, is that you want that the density of the data epsilon is upper bounded by the robustness constant gamma over the Lipschitz constant of the functions h and q. Okay, so here you can see nicely that if, for instance, your barrier function has large Lipschitz constant, so it's not really that smooth, then you will need more data. Okay. In more detail on this, let's pick the safety constraint that we enforce to be positive here. So basically, this constraint says that for all the finite number of data points that we have, we want that h is positive, in fact, greater than gamma, right? What we want to achieve with this constraint really is that h of x is non-negative for all x in our region calligraphic D, so for our safe state, right? Now, if we look at this, then we can conclude by a simple Lipschitz argument that h is non-negative for all states x that are sent or that are in this ball of size epsilon centered at the data point xi. If the condition that we enforce holds, so if h of xi is lower bounded by gamma, and additionally, if the size of the ball epsilon is bounded by gamma over the Lipschitz constant of h. Okay. And then it simply follows that we have that h of x is larger than or equal than 0 for all the points in our ring. Okay, since we have defined it as the union over all of these. Now, that allows us to generalize from finite amount of data points to the whole region that we're interested in of dense states. And you can derive similar conditions for the other two constraints, and I omitted the details over here. Now, one side note I want to make is this is a Lipschitz argument that is computationally efficient, right? There are alternative approaches. If you want to throw a little heavier machinery at it, you can, for instance, use SMT solvers to verify these types of conditions. Okay, so now I've talked about, how do we get valid control barrier functions if we have a feasible solution to the optimization problem, but how do we even solve this optimization problem, right? In general, this problem is highly non-convex, right? But we can show that under a certain parameterization of this function h, we indeed get a convex problem. Indeed, if you parameterize h as the multiplication of a vector of decision variables that you want to find, times some nonlinear basis functions, for instance, Fourier features or polynomials that you have defined a priori, then you can show that this problem here becomes convex and you can solve it very efficiently with, standard solvers. However, if you want to rely on the expressivity of, for instance, neural networks, then what we do and what works really well in practice is we take this constraint optimization problem and we define, based on that, a relaxed, unconstrained optimization problem. And we do this by a Lagrangian approach. So in fact, what we do is we take these constraints here and we put them into the cost function of the unconstrained optimization problem. So basically here we use this max reformulation and we multiply it with a Lagrange multiplier that we maximize over in an outer loop. So note specifically, if this max function here evaluates to 0, then the original constraint is satisfied. Okay. And we do this for all types of constraints that we have, and then we simply run backpropagation over this unconstrained optimization problem to find the parameters, for instance, of a neural network. Okay. Now, let me show you a toy example, just convince you that this works before we go to more complex systems. And here we have a 2D system that is actually feedback linearizable. It's a very simple system. And the goal here was simply, well, we want to track some form of circular reference trajectory while making sure that we never enter the red region over here, right? Now, first thing we need to do is we need to get expert demonstrations, right? So in this case, what we said, well, for this simple system, we know how to design a CBF already. So let's use an expert CBF that we found in some paper, looks like this. We feedback linearize the system and we simply collect data from there, okay? So in this case here, the green data that you see here is our safe data. And the red data points are the unsafe samples that we obtained. And we have some buffer region here in between that we use to allow a smooth transition of the barrier from the safe to the unsafe region. We used this convex approach that I talked about. So we, in fact, used 200 random Fourier features, okay? And we solved the convex optimization problem. And you can see the level sets here and the level curves basically over here. You see, you get this nice donut that is exactly this shape that we would be expecting with the expert data that we have obtained. And just to prove or show and check the validity of the CBF, recall that we basically had to check post hoc a condition that was something like data density needs to be bounded by the robustness over the Lipschitz constant of the functions h and q. And we need to do this for all three constraints or type of constraints that we have. You can see here that this condition holds for all three constraints. So for the h greater than 0, h smaller than 0, and for the CBF constraint here as well. Okay, so one of the issues that I have brushed over is how do we get unsafe states? Is that a question or?
I have a question.
Yes.
Is it okay if I do it now or?
Totally, yeah.
Could you please go back to one more? That one. So what happens if I've been thinking a lot. If you put a prior on theta there, then it's easy to show that that yields a Gaussian process if you put a prior in theta, right? It's basically Bayesian linear regression and it ends up being a Gaussian process. Do you think by following that Bayesian approach, you can still model or use the same framework for learning CBFs using a Bayesian approach? Since I'm asking because here you don't have the labels to train the Gaussian process, right? Let's say if I had h, the value of h at the centers of the epsilon balls, then I could just maximize the likelihood and find the parameters of the kernel. But here, since I don't have those labels to do like the training, do you think I can still, if I put a prior in theta or follow a Bayesian approach, do you think that this framework would still work?
I'm not sure, to be honest. I think we would have to talk a bit more about it, and maybe we can do that at the workshop. I'm not entirely sure how a prior there would help you or how it would factor into the problem, to be honest. Because here we simply use this as a parametrization of the function h, right? But I mean, you can include kernels there and they may give you some advantage. So in other words, if you have a different parametrization of h, I think that's totally fine. If you're thinking about that, and the approach would still work, right?
Great.
Okay. All right. So one thing I wanted to talk about is the challenge of getting unsafe states, right? You can imagine, or you saw in the previous example where we had a 2D system that you can simply sample those points, right? If you have a nice geometric structure, then you can basically sample points by hand. But this may not always be feasible. In general, it's very hard to get unsafe states that are at the boundary of the safe set if the safe set has a complex shape, or if you operate in higher dimensions, let's say higher than 2 or 3, right? So there needs to be some computational algorithm that gets samples unsafe states for you. Okay. And our idea here, and what we found to work really well in practice, is that we take safe states, so from the boundary of D, and label them as unsafe states. So instead of sampling states around the boundary, we actually look at the boundary of our safe set, and we label these states to be unsafe. Okay. And there are efficient algorithms to do that. Let me show you an example first, and then I'll talk briefly about what the algorithm does. Here, for instance, you have, well, simply Gaussian distributed data in 2D. And if you run these algorithms, you get basically the boundary points that you label as unsafe, while everything inside will be safe. And you can do the same if you have a mixture of Gaussians here. So this is just to illustrate, and it works in higher dimensions. We've used it up to 5 dimensions, actually. The idea here is the following. You will take the state, so you take all the safe data, and you take those states that have the fewest reverse K nearest neighbors, and you take them to be unsafe. The intuition here is the following, that the boundary points tends to have fewer K nearest neighbors, okay? So the K nearest neighbors are basically all the K nearest neighbors of one data points are all the K nearest neighbors, right? And the inverse K nearest neighbors are those that for a data point, how often that data point is a K nearest neighbor for another data point. And then it's intuitively clear that you will get boundary points over here. It's very easy to implement, and it works really well in practice. Okay, so this is the basic framework. And then we thought more about, well, what can we do if we have model uncertainty or state estimation uncertainty? The first one is we may not know the system dynamics F and G exactly, right? Common approach in control is that we have models, F hat and G hat, that are accurate, right? And by accurate here, I mean that the distance to the true system is bounded by some arrow bound delta F or delta G. This is a common approach in robust control. And we can easily extend our framework to this setting. Recall before that the CBF constraint here was basically the inner product between the gradient of H and our dynamics and the class K function alpha added over here. So what we now do is, instead of using the functions F and G, which we don't know, we use our models F hat and G hat. The class K function alpha stays the way it is, and we add a robustness term, simply taking, so to tighten this constraint, simply taking the norm of the gradient of H times the robustness terms delta F and delta G here on the right-hand side. And now, instead of using this Q in the algorithm to learn the CBF, we use this robustified CBF constraint. And we've implemented this in an autonomous driving simulator in Carla. Here on the left-hand side, you see a car whose dynamics are unknown to us. We had to identify a system model. We used an expert controller. In this case, this was just a PID to unroll data. And on the right-hand side, you see the robust CBF controller that we have learned. And if you compare them closely, you see that the safety properties of these controllers are actually very similar as we expect, right? Now, the good thing is we learn the CBF in relative coordinates, in this case, the distance to the center of the road. And you can simply use the controller also on different roads where you haven't collected any data, right? So here we have a different test course. We hadn't had any data of that before to train the CBF, and it still works really well. Okay, so the next issue that we focused on was state estimation uncertainty. So far we assumed that we know X exactly, the state of the system. However, as we know, typically that's not really the case, right? The specific case that we focused on was where we have high dimensional measurements, for instance, dashboard camera images, right? And usually if you use such cameras as sensors, then the sensor map P is unknown, right? It's really hard to model. But it's a realistic assumption that you say that even though you don't know P, there at least hypothetically exists an inverse map that recovers the state X given a measurement, okay? You may not know these, but if you have an image, it's reasonable that you can recover a position, for instance, here in this case, the distance to the center of the lane. And following this intuition, what we do is we train an estimator. In this case, this was a neural network and ResNet 18 that gives us a state estimate. And we again make an assumption similar to the one on the previous slide, where we assume that this state estimate is delta P close to the true underlying state that we don't know. And then the story is the same. Instead of using the CBF constraint Q that we have here, we use a perceptual CBF constraint where instead of the state X, we use the estimate X hat. So we use the estimator, both in the gradient or in this Lie derivative, as well as in the class K function. And we again add a robustness term to tighten this constraint. Basically, the error that we're making, the delta P times some Lipschitz constant that depend on or times some term that depends on Lipschitz constants of the function f, the function g, as well as the function h. Okay. So there are some more details to it, because then ensuring that you have a valid CBF becomes a bit more challenging. So we have conditions there, but this is the high level story. And we also implemented this in Carla again. So now we're taking here these dashboard camera images that we had to rescale to be able to deal with them computationally. So we only have these small images over here that we then learn to estimate such an state estimator. Like I said, this is a ResNet 18 here. And from there, we trained a perceptual CBF that you can see in action here. It's a bit more shaky. We haven't fine-tuned the controller, but it's keeping the car safe within the lane. Okay, so now what we did is we saw how we can learn CBFs from demonstrations, how we can deal with state estimation uncertainty and with uncertainty in the system dynamics. And we also looked into how we can deal with certain classes of hybrid systems. I think hybrid systems most of you are familiar with, but I still want to repeat it very briefly. You know the flow jump formalism that Ricardo is working on and has written several books on, where basically we have a hybrid state Z that follows an ODE if the state is within what we call a flow set C, right? So if we have this blue set here, the system is allowed to flow continuously. And whenever the system state Z is within the jump set D, here this purple region, the state may change discontinuously, right? And if we have an overlap of these two regions, we can either flow or jump, right? So we can do both. Standard example that I guess you're also familiar with is a bouncing ball, where the state is position and velocity. Here during flows, it follows the position follows the velocity, and the velocity is determined by the gravity, while whenever the ball hits the ground, the position stays the same, but the direction of the velocity vector changes, and there may be some foredamping involved, right? And the 2D phase portrait that we have here is, if we start from here, basically the system flows until it hits the ground, there's some damping, and then the process repeats itself, okay? So to map these hybrid systems back to learning CBFs for hybrid systems, we follow a very similar approach. We assume here that we have a known dynamics parameterized in this way. So we have functions f, c, and gc that define the dynamics during flow, and fd and gd that define the dynamics during jumps. And we have continuous control inputs uc and inputs for the discrete jumps that we call ud. And we assume here that we know the dynamics. We could again play a robustness approach. I'll do this in the very end, but for now, assume you know that. What we then need is expert demonstrations during flow and during jump. So we need to observe the system as it flows and jumps. And we need to observe the expert actions during flows and jumps, if there are any, right? So it may be that there are jumps without any control inputs. That's also fine. And then we feed them into an optimization algorithm that I'll show on the next slide. And the goal is then to learn a safe set here that again under approximates the operating region of the expert during flow and during jump, okay? So here the contributions are, we do this for hybrid control barrier functions, and then we show again how we learn them. Okay, so hybrid control barrier functions, I guess some of you are familiar with it, so I also want to repeat it very briefly. They are similar to the control barrier functions in the purely continuous case. We have a function h that defines the safe set as the zero superlevel set, given over here. And basically, the goal now is that we would like to stay inside this safe set C by suitable control actions during flow and during jump. And there's this notion of hybrid control barrier functions where we have domains, continuous domains DC and continuous domains DD that may be inside the flow and the jump set, okay? And for these, whenever we are in these continuous domains DC, we want that this CBF constraint that we've seen before basically the inner product between the gradient of h times the dynamics, is lower bounded by minus alpha of h of z. So this is the same condition as we had before. But now we also need a condition that holds during jumps. It's very simple. Actually, whenever we're in this discrete domain dd, then we want that we can find a discrete control input ud such that after a jump, h is still non-negative. Okay, intuitively quite easy. In the remainder, I will refer to the first constraint as the flow constraint, and as the second constraint, I'll refer to as the jump constraint. Right. Now, we need to again talk about safe and unsafe data. It's a similar story as before, but now we have safe demonstrations during flows and during jumps. So what we're doing is basically for each data point during flow, we put an epsilon c ball around it, and we again take the union so that we get this black region denoted by DC. So this is our domain that we have data in. And we do the same for all the data points during jumps. We put an epsilon ball, epsilon of size epsilon d around it. We take the union over all these points, and then we get this discrete domain calligraphic dd. Okay. And additionally, what we need is we need, again, unsafe data points that we either sample around the union of these two domains, dd and dc, or we again take a computational approach that I elaborated on before. Okay. So the optimization problem that we know right down is similar to before, but we add another constraint that enforces the CBF constraint during jumps, okay? So we again enforce that h is negative for all unsafe data points. We enforce that h is positive for all safe data points, where safe data points are now defined as the union, again, of the demonstrations during flow and during jump. And then we enforce the flow constraint for all data points, all safe data points during flow. And we enforce our jump constraint for all data points during jumps, okay? And note again that you enforce these constraints with a robustness slack gamma, here denoted by gamma dynamic D and gamma dynamic C, okay? If we can solve this problem, and solving this problem is actually really almost the same as before, just taking care of this additional constraint. And if we have a feasible solution, then we find a safe hybrid CBF under very similar conditions. So we again need safe data points. We need the functions h, qc, and now also qd to be smooth enough in terms of the Lipschitz constant. And we need large robustness slack. Okay. So with that, I mean, we can go into the first case study, first an academic one. We have the bouncing ball, but here we artificially inserted some control inputs. So during flows, we have a control input UC. You can think of it as a controllable wind resistance. You know, we made something up there. And also during jumps, you can control the floor damping here by UD, okay? And our safety specification here was basically that we want that the velocity never exceeds 2 in absolute value. Okay, so first we needed to get some expert data. We used some controller for that, which you can see here. So in purple, you see the expert demonstrations during the jumps. In green, you see the expert demonstrations during flow. And then you see the unsafe data points that we sampled here given in red. From there, we trained a hybrid CBF, and the level sets, they're basically shown in this figure. So we see exactly what we would like to see. And we tested the CBF as well in this case. In fact, we asked the CBF, or we asked the system to track this blue but unsafe trajectory, and we wrapped the safe hybrid control barrier function around, and you can see the barrier function kick in here basically to keep it within the safe set. Okay, so it's only following this blue trajectory as much as safety allows for it. The last case study I want to show is on a compass-gazed walker. So we have this hybrid walker that is walking down an inclined ramp. You could control the system in the hip and in the ankle joint. If you don't do that, it's known that there's only a very small set of initial conditions from which the walker will walk safely down the ramp. Usually something like this happens. So if you don't apply any control input, the walker will just fall down after a couple of steps. It's basically unsafe. So what we did here was we used an energy-based controller from Russ Tedrake's textbook as an expert. to collect some data. And we use this data to train a two hidden layer fully connected neural network, okay? And this two hidden layer fully connected network that defines a hybrid control barrier function is shown here in action. So you see the control action, the correcting control actions in green, in the hip, and as well as in the ankle, okay? So I can repeat this again so that you see that whenever the agent corrects itself, it will still stay safe. And the level sets here over the evolution of the system is shown here. So H always stays positive as desired. I would also like to show a more quantitative analysis here. So on the right-hand side, you see the energy-based expert controller. On the left-hand side, you see the learned CBF, hybrid CBF controller. It's a 4D system. So what we did here is we fixed the initial position and the angular velocity of the left leg, and we varied the initial conditions, so the angle and the angular velocity of the right leg. Okay? And each data point that you see here is one initial condition from which we unroll the system. And if this point is blue, it means that the walker walked more than 10 steps, so it's considered safe, while red indicates that it fell before that, so it's unsafe. Okay? And what we show here in this 2D slicing of a 4D system, so it's a bit visually distorting, but we show here the sliced zero level set. What we can observe here is that the data points, most of the data points in there are safe, right? They are blue. And importantly, this is the expert controller on the right-hand side. And on the left-hand side, our learned controller has roughly the same properties. In fact, what we found out here is that in some regions where the expert is doing quite poorly and is unsafe, the learned controller is actually doing better than the expert. And the potential explanation for that is that we induce some robustness during learning. You remember these robustness legs gamma that tighten kind of the CBF constraint? That is exactly inducing some form of robustness that is helping us here already. And lastly, I want to talk about how we can even learn robust hybrid control barrier function. It's a similar idea like before. So we assume models of the hybrid system, and then we define an optimization problem from which we learn the CBF. I just want to show some examples here. We again have the hybrid walker, and we put some additive disturbance on the dynamics during flow. The learned robust controller is shown here for different levels of noise that we put on top. So during training, we used a delta C of 0.25. But you can see for all of these that the controller is doing really well. Here's a legend basically down here that shows how many steps the walker walked from this initial condition. So red is doing quite poorly, while green and blue is more than 10 steps. And you can see a lot of green here. So this is doing really well. While the expert controller, the energy-based controller, is actually doing really poorly especially for larger delta Cs, right? You can see a lot of times that the walker is falling down. So inserting robustness here really helps in the learning. And we also made one case study where we assumed that the mass is unknown of the walker. So we had a nominal mass of 10, and I think we had a delta of 2. And you can see here that the robust CBF is actually doing really well. A lot of green here, a lot of safe walks, while the expert controller, especially for the mass of 6.5, is doing very, very poorly and is only working under nominal conditions quite well. And that was basically the talk. So I have a couple of references here that the talk was based on. And I would also like to thank the main collaborators here, which is Nikolai Matny, who is at UPenn, Stephen Tu, who just joined USC as a faculty member, as well as Alex Ruby, Hyman Hu, Satya Das, and Li Yun, who helped also with the simulations. Thank you so much. Right. Any questions?
I have questions. Can I do it? Can you hear me?
I can hear you, yeah.
Oh, yeah, thank you. Thank you for your lecture, and I'm very interested in your data-driven method to how to learn the CVFs. But my question, I have two questions. First one is there any restrictions on the control action, like the set you referred to as expert actions? the set of set with calligraphy U, is there any restrictions? Like, is it the whole space of Rn, or just restricted to? Can it be restricted to a smaller one, like a compact set?
It can be, yeah. I think that's one of the advantages, that you can assume that you have input limitations for the system, and the restriction would be that the expert needs to adhere to these input limitations, right? So you need to, let's say you have a compact set of a given size for your control inputs, then you need to assume that the experts will basically only pick actions from this compact set, which I think is a reasonable assumption. And under this assumption, you also get a CBF or a hybrid CBF that respects these input limitations. I think that's one of the benefits, because in general, in nonlinear or also hybrid control, of course, it's really difficult to come up with feedback control laws that respect given input limitations. But here with this approach, since you have, if the experts have, respect these limitations, you kind of actually get this for free, that you can satisfy input bounds.
So, yeah, thank you for your answer. But is there any problem that may occur in the control form reconstruction of the controller? Is there any problem when we restrict the set U as a compact one, or?
No, that's not in general the problem. I think you can also, so what you get, let me maybe go back a little. Right, let me go here. What you generally want to do, like, let's say you have found a CBF, right? When you execute the CBF, what you're looking for is, you're given a state and you want then to pick a U that satisfies this inequality, right?
Yes.
And it doesn't really matter if there is a compact set calligraphic U here, or if it's RM, let's say. What may make a difference, though, is you may not be guaranteed that the control input that you synthesize this way is a continuous signal, right?
Oh,
so
yeah.
usually what you want is, you want that the control input that you get out of this is continuous, but that is more an issue of, if the optimization problem that you write down, usually you have these you have quadratic problems where you want to follow a desired control law subject to this constraint, right? And the question is more, is this quadratic program, does it give you continuous solutions? And that's an issue on itself, where, of course, if you have input limitations, it may make it more likely that you have discontinuous controllers, right? But just for learning valid CBFs, it doesn't really matter if you have a compact set here or not. And again, if the experts adhere to the compact set, you basically get for free that you can deal with input limitations in this framework, at least, right?
Okay, thank you for your answer. And can I do one more again?
Sure, yeah.
My second question is about the input, the measurement of the function y included, y equals px, or like, in that case, we usually use the pre-image of the we just measure the first component of the state vector. In that case, the pre-image it consists of infinite number of the state vectors, right? So in that case, it can be very difficult to fix a pre-image as a single element. So in that case, in those kinds of general cases, is there any method that can be extended from here to deal with such a problem?
So let me see if I understand the question correctly. So you mean that usually you need to compute the pre-image of p hat, right?
Yeah.
It
cannot be a single element, right, in general.
Yes, that's true. So ideally, what you want to do is, you want to compute all the x's that kind of satisfy this bound given a measurement y, right? right? I mean, you have an X hat here. So I mean, what you get in practice is this will be a vector that is given to you, and you get a set of X that you need to evaluate the CBF constraint over, right? So let's say if you have this as your CBF constraint and you want to ensure that this is greater or equal than 0, then you want to make sure that all X that satisfy this inequality here also like satisfy the CBF constraint, right? So I don't think that in this formulation you get an infinite set that is bounded though, right?
Oh yeah.
And what we do in order to deal with that is that's where a bit of we take out complexity, but we get conservative, is we do a Lipschitz reformulation. So in order to not evaluate over all the infinite kind of x's that are in here, where you take the infimum over all the x that satisfy this constraint, we do a Lipschitz reformulation. So you see you have the delta p over here that kind of captures all the x that are, that satisfy this inequality. And then we get Lipschitz constants basically is very small. Otherwise, this becomes extremely conservative. So in summary, what I was saying is instead of taking the worst case over all the x that satisfy this inequality, we do kind of a computationally more efficient variant where we use Lipschitz constants that comes at the cost of conservatism.
Okay, I understand that. Thank you for your.
Lars, I have a question. And it's regarding the construction of your set of expert or like set of values. Probably it's like 10. Yes, this one is like number 10. When you were setting up this optimization problem. So what I understood that you do is by taking trajectories from experts, you can select pairs of states and inputs that you consider that are safe, right? And
yes.
in all the values that are taken from those points, then you construct your set of expert inputs and expert states, or like at least safe states. But it seems to me that there is a unique correspondence of actions to states that will imply or guarantee safety. So I'm a little curious about specifically the boundary of the safe set. If you do what you have in the third constraint of your optimization problem, in which you have a Cartesian product instead of the original set of expert pairs, you take all the inputs and you do the Cartesian product with all the states, then you might be taking an input that was not the original safe input to a state that is in the boundary and might violate safety, except if
I think I may be using maybe the wrong so you don't mix xi's and ui's. You have unique combinations. So in one state you have one control action that will ensure safety. You're not mixing the xi's and ui's. Was that clear, or did I just want to clarify that?
Or maybe just the notation in that.
I think it is actually. So I think this is only saying that this is the space of all, actions and control inputs that you can have.
Right.
And it's really the notation. I should have been. So you only take the ones where, like for a state xi, you use the corresponding ui only, not the ones that correspond to others. That's actually a really good observation. It's the notation here is wrong. Yeah.
It makes sense. So when you create your safe set, you're also extending the region from where you actually obtain the trajectories to states that were actually not visited by the expert, right? So there are points in that safe set that were not necessarily visited, but were included by doing the epsilon net that you propose, right? So in that case, do you allow any of the inputs to apply to any of the states in those unvisited states?
Yes. Yes, that's a really good question, because what the analysis contains is basically for all the states. So let me go to the next slide. That's where I have written it down. So kind of, well, this is, I mean, you do a similar argument here where you say for, you want that h of x is greater or equal than 0. You
Right.
want to do a similar statement for q, right?
Right.
In fact, what we're doing is we're saying q of x comma ui should be greater than 0.
Right.
So we're kind of saying that for all the x's in this epsilon ball, the same control input should help us to be safe, right?
Correct.
So and under that assumption, you can do it. And that's also why I was saying earlier that this is the reason why you will ensure that the CBF that you learn will adhere to being in a compact set if the expert does. Because exactly here we assume q of x, all the x in the epsilon ball, comma ui. And that's, of course, making an assumption, right? It's saying that, for all close by states, the same control action will be safe, which may not be the case, but may be a reasonable assumption in practice, right?
I hear you. So yeah, what I'm kind of thinking as a conclusion of this discussion is that it might be the case that you find a feasible optimization problem that you evaluate at the points that were provided by the expert demonstration, but that once you construct the bigger safe set, it might be the case that some of those safety constraints can be violated if they're evaluated in those inputs, unless you craft an example that is kind of like really carefully put together.
Yeah.
So the inputs don't affect the boundary, right?
I think it's the other way around. You will, when the optimization problem is feasible and the CBF is valid, you will always find a control input if you're in this set. So there is, whatever state you're in, you will be able to find a control input to stay safe. And this may correspond to the expert action.
Right.
In other words, if you're in this epsilon ball, right?
Yes.
If during execution, if you're in here, you're guaranteed that UI is a safe control input.
Correct.
So everything is fine.
Oh.
I think the downside of this is rather that you may not find a control barrier function. The optimization problem may not be feasible, even
Yes.
though there may exist a solution. So in a way, you lose completeness at that point, right? Because you take a kind of, I don't want to say conservative argument, but you make the assumption that UI applies also to all states in here. Yeah, exactly.
Yeah, and if you have multiple points of the state trajectory that have different inputs, then there are some like mismatch of that, right? But that's good. That's good. Awesome. Yeah, thank you. That was the question I have.
Yeah. I mean, that's a really good question, because that's kind of something I only realized when doing the analysis, when I had to fix the UI, really. Because you don't want to search over any UIs there, and it makes life easy in the analysis, but it might be a conservative assumption. Yeah.
Awesome. Does anyone have any other question?
I have a question.
Yeah.
I'm wondering, it might be kind of related to Santiago's question, but what if you have just if you don't have any good expert demonstrations, can you maybe use this to can you generate them somehow? And I'm imagining something where you could start with just really bad expert demonstrations, feed it into this to get something better, and then kind of do something iteratively. But then also there's the question of if you have bad, they could be bad in the sense of not very safe, or they could be bad in the sense of they don't explore a state space very well.
Yeah, I mean, this is something we started thinking about, but we have some conditions to what constitutes a good expert. And a good expert is that goes away from the unsafe region perpendicularly, right? Because then the inner product of the gradient of H and the dynamics, they're, perpendicular. You get the most informational gain out of that. But this whole framework really relies on a binary, safe, unsafe classification. And there's no notion of, levels of or quality of experts. And that's something actually that may be really important to explore, especially in an online context, right? where you may not have good experts. You may want to incorporate more data that you acquire online, or you may have different experts that you want to use. So yeah, that's something we haven't looked into too much, but it's a very valid question. Yeah. Also, one thing I guess this was maybe obvious already, but the expert, like the data that you have strongly influences the conservatism of the barrier, right? For instance, in this case, the barrier function is given by the size or the volume that the expert has explored. And it's natural that everything inside here is also safe, but it's being labeled as unsafe, right? I mean, if you're starting inside the donut, there's no way you can escape and become unsafe. But the algorithm will actually label it as unsafe, and you will not be allowed to explore this. So, you really rely on experts that cover huge volumes of the state space, right? So there's some work we're preparing right now on how to do this online, how to use the barrier that you have already to explore the boundary and see if you can grow the region where you're safe more online, right? And then the question is, well, how can you patch together different valid barrier functions? And there are some interesting questions actually doing that. Yeah.
Awesome. Thank you. Do you guys have any questions? Okay, let's thank Lars for.
Thank you so much for joining and also for the invitation. And looking forward to meet at least two of you on Monday, also in person in Hong Kong.
Yes, awesome. Well, if you want, you can take 5 minutes if that's something that you want to do, and then we can meet back again for a short meeting if you're okay with that.
Sounds good. Sounds good. I'll just get something to drink. I'll be back in 5 minutes.
That's perfect. Yeah.